Hello, and thank you for joining us. Today's webinar is Introducing Green Chemistry Analytical Techniques Applicable to the Teledyne Leeman Labs QuickTrace M7600 CVAA system. Our presenter today is Jeff Forsberg, Product Technical Line Manager for Teledyne Leeman Labs. Okay, Jeff, turning it over to you.
Hi, everybody. I'd like to, again, thank you for joining today's webinar. I did review the attendee list, and I saw a fair number of people that were the names I recognize. So again, thank you to everybody for joining today's webinar. So today we're going to talk about the M7600 and reducing liquid flows and waste flows on that system, more in line with the green requirements for reducing waste generation and things like that within the laboratories, in today's laboratories. A little bit about our beginnings. So in 1991, Leeman Labs introduced PS200, which was one of the very first standalone mercury analyzers on the market. In 1995, CTEC Technologies introduced the M6000A, which was a competitive system for standalone mercury analysis. And then throughout the years, we've been introducing a number of systems to help with your daily activity and mercury analysis. In 2004, Teledyne Leeman Labs was acquired by Teledyne acquired Leeman Labs in 2004. 2007, we introduced the Hydra 2C, which is a combustion system, and then various other systems throughout those years. And in 2013, Teledyne acquired CTEC Technologies, and since then the product group has been merged and to what we have today. In 2017, the CTEC systems were introduced with 560 and 280 auto samplers. Some of the highlights for the Teledyne Leeman Labs mercury analyzers, again, we have 4 models: the CVAA systems, the Hydra 2AA, the M7600, the M8000, which is atomic fluorescence and atomic fluorescence with gold, and then the Hydra 2C, which is a combustion system. We have a patented gas liquid separator for the QuickTrace systems, which the patent expired in 2016. The QuickTrace systems have a 4-channel 12-roller pump. All systems have superior dynamic range. The software on the QuickTrace is extremely flexible, and the Envoy and the QuickTrace have overrange protection. We have gold trap reagent saving costs in the M8000, the CVAF system. Auto sampler configurations for the 2 QuickTrace models, and then the Hydra products are modular, which is a nice feature, and then 25 plus years of brand recognition. So the 7600 is our most versatile CVAA system. Detection limits at less than 0.5 nanograms per liter, and that's in the most sensitive mode of operation. And with that system, we do have the capabilities of achieving the method detection limits for US EPA 245.7. The method detection limit is, as I recall, it's 1.8 nanogram per liter. But I have to warn everybody that we need to run this with caution. With the BRCL, the bromine monochloride, which is the solution for oxidizing the samples, it will form bromoform. It has a possibility of forming bromoform with certain samples, and that organic compound will absorb at our wavelength at 253.652. But with that said, the system can hit achievable method detection limits and reporting criteria for that method in less than 90 seconds. And that's achieving a less than 1 nanogram per liter MDL with the method. Typical range for the system as received is 0.5 nanograms per liter to greater than 500 micrograms per liter. And that's our release specifications, and this is with no hardware changes. So the QuickTrace M7600 is a double beam system. So we have double beam optics, lamp stabilization. So that is a thermally stabilized lamp compartment, optical feedback for the electrical optical feedback for the lamp control. And what this will do is, as the lamp ages, it senses the radiation coming off the lamp, it bumps the power up, so during the lifetime of the lamp, our IDL or MDL doesn't change. It's a very nice feature, so when the customer is using their M7600 day in and day out, they're going to achieve the same response for the same standard. Computer-controlled gas flow. It's a mass flow controller. The system is designed and optimized for argon, but it'll also work for nitrogen, greater than a liter per minute argon flow. But since it's optimized for argon, the nitrogen will not quite achieve a liter per minute. It's more in the range of 750 milliliters per minute. Gas liquid separation. So I mentioned earlier about the patent on the GLS, or the gas liquid separator, which expired in 2016. So this is a center post design, and that's a large reaction surface area to our liquid volume. So when it's running, it looks like it is running basically empty. You're going to see a small amount of liquid at the drain port, and that's about it. So what this system will do for the customer is increased efficiency. That'll increase your throughput. It gives you a stable liquid film, liquid flow, and that in turn is reproducible signals and precise results. So when you take the reproducible signals and precise results, then that affords the customer that ultra-trace method detection limit. So it all starts with the gas liquid separator and our mass flow controller, our double beam optics, and then the 4-channel 12 roller pump. So the theory of operation. So the samples all have to be acidified. So everything has to be digested. So the mercury's in Hg2+, and then the sample is delivered by the auto sampler to the gas liquid separator. So en route to the gas liquid separator, our reducing agent, which is 10% stannous and 7% HCl, that already reduces the acidified mercury in the sample to Hg0. From there, we introduce our gas flow. So our gas flow is flowing through the dual beam optics. So it flows from left to right, flows up and around, and then comes in and goes into the bottom of the gas liquid separator. The elemental mercury at this point is already reduced, so it's easily stripped off, and from there it flows into the Nafion dryer, where the water is removed and it's off-gassed into the laboratory. It's just water vapor, and the carrier gas, which is argon, and it's laden with mercury, that leaves the dryer, and it goes up into the sample cell. And in the sample cell, the gas flow moves from right to left, so it's counter from the direction of the carrier gas, and this is going to measure the absorbance at 253.652. The detector is a CCD, so we have 2 beams and collimating light through the sapphire windows, and then off to the detector where the light is filtered and the absorption is measured. The M7600 has very broad linear ranges, greater than 4 orders of magnitude. So our typical dynamic range for the system is 0.5 nanograms per liter to greater than 500 micrograms per liter, or ppb. So here's an example of the orders of magnitude of linearity. So we're achieving 3 9s and an 8 9, and here's the values from this curve. So we went from a 1 nanogram per liter, 1 ppt, up to a 10,000. So here's the first order at 10 ppt, 100 ppt, 1,000, or 1,000, and then a 10,000 ppt, or a 10 ppb. And you can see the response. The response is very linear, greater than 3 9s. So now that all of this has been discussed, how the system, the basic theory of the system, what affects this dynamic range? How can we get such a broad dynamic range with this system? So it's gas flow. gas flow, pump rate, and time in sample. So if we adjust the gas flow, high flows will equal a short residence time, and that gives us speedy results, but it decreases sensitivity. So again, decreased sensitivity, we expand that dynamic range. Low gas flows are long residence times within the optical bench, optical cells, and that will increase the sample times, but it increases the sensitivity. So if it increases the sensitivity, we are decreasing our IDL and our MDL. Pump rate, same thing. It'll increase or decrease time to the GLS, and that changes the mercury load within the system that is taking the HG0 and sending it off to the optical system for measurement. So that changes our flow. So gas flow and pump rate, and now time in sample is the third leg of the stool. So time in sample to adjust a steady state for a flat signal on the plateau for peak height. We can also use peak area. So if you want to just measure everything under the curve, your peak signal will be similar to like a liquid chromatography peak and such, and it will be everything under the curve. You can go really, really fast. We can typically run samples less than 60 seconds and more in the range of about 50 to 45 seconds. So you adjust all three of these settings to achieve your desired result. So again, 3 steps: change the gas flow, change the pump rate, and change the time in sample. So what are the advantages of this 12 roller 4-channel pump? So the original tubing harness gives you UltraTrace method detection limits. The sample's not consumed, so you can go back and check out the responses from samples that may be in question, so you can allow repeats and validation checks. You can also dial in the flows for high concentration or UltraTrace analysis. It gives us wide dynamic ranges, and the liquid uptake is from greater than 1 milliliter at 5-second sample to a max rate of 15 milliliters per minute, and that's at 60 seconds of uptake time. So if you haven't guessed already, the max rate at 100 RPMs is 15 mils per minute with the current pump tubing that we're using. So the original pump tubing, parallel channels are for the drain. So channel 1 and 2 are using yellow. The ID is 1.42 millimeters, and the part number is SP5705A. For channel 3, which is this one right here, that's still yellow, same ID at 1.42, so same part number. And channel 3, which is black, that's our reducing pump tubing, and that is 0.76 millimeter for the ID, and the part number is SP5705. So why do we have 4 channels and 3 are the same? So we're pulling sample in and then pulling reagent in, and we want to ensure that that GLS runs empty. So we exceed the input of the volume with the output going to the drain. So we make sure that the system is empty at all times. So the alternate pump tubing, this is now where we get into the green chemistry. The introduction alluded to green analytical. So the advantages now are still, we have UltraTrace detection limit. Still the sample's not consumed, and you can do the validation and checks of existing samples already previously ran. You can dial in your flow concentrations for UltraTrace analysis. That's still in play, but we have a wider dynamic range, and that's simply because we're using less sample. Less sample is part of the 3-legged stool. We're going to be changing the process slightly, and we're going to increase the concentration by reducing the sensitivity of the system. Liquid uptake is 0.5 milliliters, and 5 seconds is our minimum, and now our max flow rate is approximately 10 mils per minute, 60 seconds at 100% pump rate. The alternate tubing harness, channel 1 and 2, the part number is 15-43 08-102, and our ID of that sample tubing and waste tubing is 1.02 millimeter. Channel 4, which is the reducing, is part number 15-4309-102, and the ID is 0.51 millimeter. This is an extremely small ID tubing, so in order to have it compatible with some of the fittings and barb fittings that we use on the system, we had to have it flared. So this tubing is a small ID, but it's flared, so it holds its flare and it allows the customer to attach it to the tees and capillaries and so forth. So the alternate pump tubing at 100% rate, as I mentioned earlier, we're now at 10 milliliters per minute. That is 67% of the flow from the standard tubing. So 33% savings right off the bat. The reagent went from 0.57 milliliters down to 2.7. So that is 47% of the standard tubing. So it's a 53% savings on flows. So our combined flows with the new tubing harness is 40% on combined flows for waste. So that's including the stannous chloride and the sample. So the waste generated is approximately 40% less. At 100% pump rate, that gives us a reduction in stannous chloride because we're 53% less, about 47% of the standard flow for the reducing agent. That's 180 milliliters per hour. So if we look up some of the standard pricing for stannous chloride dihydrate, 500-gram bottle could be anywhere from $400 to $600 per bottle MSRP without your discount. So let's just assume $500 a bottle, so 10% stannous in a liter of solution during an 8-hour day. That's going to save us $150 US because we're actually saving 1.4 liters. And if we multiply per day by 5 days a year, 52 weeks in a year, that's going to give us an overall savings of $39,000 US in stannous chloride alone by going to this green chemistry with the alternate tubing. So at 100% pump rate, also that gives us 470 milliliters of waste reduction per hour, which is also costly to dispose of waste. Reduced flows does result in a very slightly a very slight increase in instrument detection limit. We are now at less than 1 nanogram per liter, so that's up from 0.5 nanogram per liter, so not a lot, but a slight due to the decrease in sensitivity. But that decrease in sensitivity does allow for a larger dynamic range of the system. So the flows are very linear. So with the new tubing harness, we tried all different pump rates and different scenarios, and we tested for many months of the system, and they pretty much average out to the same. So the reduction in sample uptake is about 33%, and the reduction in reagent is about 53%. So here's at 80% pump rate, and sample is 12 down to 8, and the reagent is about 4.5 milliliters per minute down to 2.2 milliliters per minute. So again, 53% reduction. That's where the big savings is going to be in the stannous chloride of this system. So here's an example of liquid flows for waste at 50% and 80%. So 40% reduction. So we're at 10 mils per minute. Liquid flow waste down to 6, or 6.4, so approximately 40% reduction. And here is 50% for the stannous at 2.85 and 1.35. So again, about 53% reduction in stannous chloride flow, or 47% of the original flow. Same thing at 80%, we're 16.5 down to 10, and then 4.6 down to 2.2 for the reagent flow. Method development. So you're going to obviously have to do some method development with the new tubing, but method development is relatively easy. So we have our method editor on the favorites bar. So in there we have file, tools, conditions. Conditions is where you're going to spend most of your time. So this is controls for the auto sampler and the analyzer, method timings and settings. So uptake, baseline corrections, peak reads, and so forth. We also have our standards and our QC tests are all lumped into the method editor. So in Method Editor, under calibration, under standards, that's where you enter your calibration parameters. You can pause pending, and the system will also even email you once the analysis for the, once the analysis for the calibration is finished. So in the method editor, you can do things like fill down for your standards. You can enter in your peak height, your quantitation type. So it's peak area, peak height, and then your quantitation type is your methodology and so forth. And it's really easy to fill these down. Real-time method editor, you can do things like enter in your quantitation for your systems. So units of measure, weights of measure, and units of volume. So we allow for these things to change within this method editor. And this is set up for laboratories that may be using different units of measure. So like a biological lab, a pharmaceutical lab, university, and so forth. So in biological laboratories, it may be units of measure, maybe milligrams per deciliter or millimoles per deciliter, and so forth. So you can create your own methodology and your own reporting criteria and put it into the system. So it's very, very flexible, and you can also change your standard names and so forth in this method editor. So in method editor, we also have under conditions, now this is where you're going to enter in your timing for the system. So in your timing for the system, you have auto sampler, so it's time and sample and rinse time. And then under analyzer, you're going to have your timing for that system as well, which is your pump speed, your gas flow, read delays, time and sample replicates, and your baseline correction points. So this is all done in real time. When you're doing your method development, above the graph, we have the favorites bar for this, and this is toggle your grid lines, copy chart to clipboard, print on Zoom, peak profile, so that's a single sample read, stop, start, and copy your profile to the worksheet log. So basically you load your sample up, you go to a single sample, and it reads it, and this is in real time. So in real time we can take and adjust the integration points and the baseline points to make changes for the method development, and you can add them in here under method editor, under analyzer. So you can do things like you can grab the read delays with your mouse, move them from left to right, or you can just simply bring them over here, and you can type them in or you can toggle them up and down. So when that happens, you can take and see how the method is working for you based on your relative standard deviation for the peak height of that sample. So once it's all done, so here's how it works. So you have pump speed, gas flow, sample uptake, rinse time, integration time, baseline correction points. So you peak profile. So you want to use your highest concentrated standard to do the peak profile, because everything will fall in line underneath that. And then you adjust all your timings for that stable signal on your peak height. So you very simply run it, and you can look at your graph, and then you can adjust your baseline correction points and your peak integration for your lowest percent RSD of that peak height. And this is all done real time. It takes maybe a minute to 2 minutes to develop that profile, and then you're ready to go with your calibration. So for the pump tubing, the reduced ID pump tubing, we've set up a couple of basic methods to start. So this one is 0 to 100 nanograms per liter, and the range for this is less than 0.5 nanograms per liter up to about 100. Gas flow is 40, pump rate is 100%. Our sample flow is about 10 mils per minute, and our rinse for our auto sampler is variable up to 100%. So we need to have a positive rinse flow. So if you have positive rinse flow, you're flushing the system better, you're not pulling air into the system, you're going to get more stable results. Sample uptake for this was 60 seconds, and our rinse time was 100 seconds. So our total analysis time is approximately 160 seconds. Our read delay was at 74 seconds. So the read delay is right here. This is where it's going to take the information for the peak height. We're doing 4 replicates, 2 baseline correction point for this. And our response is about 4,000 microabsorbance units for 100 ppt. So that gives us a slope of 40 microabsorbance units. And the slope is for each ppt. Total analysis time was about 2 minutes and 67 seconds. Here is 0 to 20 ppb, microgram per liter. This is a typical range where most laboratories will be operating in. Most of your methodologies that environmental labs and so forth will be running is in ppb range, maybe 0 to 5, 0 to 10, or maybe even 0 to 20 microgram per liter. So this one is set up for 0.1 to 20. Gas flow is 100 mils per minute now instead of 40. Pump rate went to 50% instead of 100. So as I mentioned earlier, it's very linear with these flows with the new tubing. So now we're at about 5 mils per minute sample uptake. Rinse time up to about 60% variable. That's going to give you your positive rinse, so you're not pulling solution out of the rinse station faster than it's supplying. Sample uptake time is 55 seconds and rinse is 110 seconds. Obviously, we have higher concentration, so we want to make sure it's rinsed out to baseline. Read delay 77 seconds. Replicate time is 2 seconds. Our response is 135,000 units for a 10 ppb, so that's given us a slope of about 13,500. And with that, our nominal detection limit of this method is going to be less than 0.01 microgram per liter, or less than 10 ppt. Sample time is about 275 seconds. Now, one thing with the single baseline correction point, you can run much faster. So if you notice here, let me zoom in and I'll give you a quick preview of this. So in here, if we zoom in, we look at the baseline. So the peak starts at an inflection point of about 50 seconds. So we have all this extra time up front. So we could take that out of the rinse and have it coming down to baseline here, as long as it's at baseline before the integration point. So instead of having a rinse time of 110 seconds, that rinse time could be 80. So we could take 30 seconds of analysis time just by utilizing the front end coming down to baseline before that baseline correction point. So there's lots of ways to increase the efficiency of the system. So typical performance with the new tubing is 0 to 100. The trace range, gas flow is 40 mils per minute. Our IDL is less than 0.8 nanograms per liter. They were coming in around 0.6 to 0.7. So it's definitely less than or less than 1 nanogram per liter. Short-term precision at n equals 5 at a 5 ppt is less than 3%. 20 ppt at n equals 5 is less than 2%. The response is 40 microabsorbance units per liter, nanograms per liter, and the ppb range, our IDL is less than 10 ppt, 0.01 ppb, gas flow is 100, and the precision n equals 40 is less than 2.5% at a 200 ppt or 0.2 ppb. And again, the response, our slope is about 13,500 units per ppb. So to validate the tubing, we used two different methods. One was US EPA 7471, which is from your solid waste manual 846. It is for soil sediments, bottom deposit, and sludge type materials. Our calibration was 0.2, 1, 2, 5, and 10 ppb. The samples were approximately 2 grams and 50 milliliters, and this is done by block digestion. For the other half of the sample base, we used US FDA EAM 4.5, which is the elemental analysis manual, and this is microwave assisted digest. These were some of our food samples, and the calibration was 50, 100, 250, 500, and 1,000 nanograms per liter. And the sample is approximately 0.5 grams in 50 milliliters, and again, it's microwave digestion. So the two methods, the 7471, here's the system parameters. So our uptake is at 35 mils per minute, and the gas flow is 100, rinse time is 80, pump speed is at 50, and here's our integration. So remember, it's very, very linear, so pump rate at 50%, so now that's going to be, instead of 10 mils per minute, it's approximately 5 mils, and with our timing, we're about 3 mils per liter of sample uptake, and our Stannis is approximately 0.8 milliliters at 1.35 for the full rate, and total waste now is less than 4. For the FDA method, we are at 30 seconds of uptake, but 80% pump speed. So that gives us approximately 4 mils per minute and 1.1 of the Stannis, so less than 5 mils per sample, total sample load of waste. The samples that we use for validation: laboratory control sample, a laboratory control duplicate. We analyzed some over-the-counter salmon, duped it, and also over-the-counter crab. And for tuna, oyster, and mussel, we had CRM's SRM type material. For the EPA method, for the sediments and solid waste, we had fly ash, Tennessee River sediment, industrial sludge, and coal. The Tennessee River sediment was relatively high at 50 ppm, so we diluted that by 50 prior to analysis on the system. CRM recoveries were very, very nice across the board. Two different methods, two different digestion techniques. The lowest response percent recovery was 92.6. So here's the concentrations, just for reference, of those samples. So both the US FDA and the US EPA methods performed very nicely as expected with the new tubing. And one of the reasons for this is we did not change the ratios of sample to reagent usage. The ratios are almost identical, so that didn't change the kinetics of the pump rates and the gas, the reduction of the Stannis for the mercury from Hg2 plus to Hg0 within the gas liquid separator. Spike recoveries for the food samples were really, really nice. So the salmon and the FTA, lowest one was 86.4. So the salmon, the raw, was a result of 0.0113 ppm, milligrams per kilogram. If we assume 100% conversion to methyl mercury, that is 0.0121 milligrams per kilogram methyl mercury. For the crab, that came out to 0.0084 milligrams per kilogram methyl mercury. So based on the World Health Organization, they say 1.6 microgram per kilogram per body weight is what they allowed per week consumption of methyl mercury. So this turns out to be 0.0016 milligram per kilogram ppm. So that would mean that an average male in the world is 80.7 kilograms. They can consume less than 0.129 milligram per kilogram of methyl mercury tainted food and still be relatively okay based on the World Health Organization. Average female is 76.4 kilograms, so they can assume 0.1222 milligram per kilogram. So if you look up here, you could eat the whole entire kilogram of salmon and or crab and still be okay. It's a lot of food, but based on that organization, you would be fine. The US EPA, they have a little tighter regulation. Theirs is 0.0001 milligram per kilogram body weight per day. So if you take that by 7, we're still slightly less than the 1.6 milligram per kilogram per week. Combined results. So the CRM and SRM spike recoveries were very nice. This is an aggregate, just a top level view left to right of all the performance of the system, percent recoveries. So everything is above the 80%. Lowest spike recovery was 86.4, but then all of the recoveries for the SRMs were well within the range. We like to see the up and down below 100%, which tells us that the system is performing as expected. So if you have everything above the nominal range of 100% or everything below the range of 100%, I would tend to look for some type of analytical problem or a determinate error within the system. Summary of the pump tubing. So the flows for the standard ID, 15 mils per minute. So we went from 15 milliliters per minute down to 10. Stannous chloride went from 5.7 down to 2.7. Total waste at 100% rate went from almost 21 milliliters per minute down to 14 milliliters per minute. And the variable rate for the uptake, the lowest we picked up before at 5 seconds is 1.25 milliliters. Now we're down at 0.8. Detection limit did change slightly, again from less than 0.5 to less than 1. And typically with the standard tubing, instrument detection limit on the system is around 0.2 to 0.3 nanograms per liter. I say less than 1 here, but we were like 0.6 to 0.7. So it is basically double of what the other one was, but we're changing the rate, but we're still less than 1 nanogram per liter, which is much better than a lot of the other systems on the market. Usable range, we did increase slightly up to 700 ppb, up from 500, so an increase of approximately 200 ppb. And then the performance specifications, they really didn't change all that much. So 3 to 3, 2 to 1, 2.5 to 2, that's relatively the same. The only thing that did change was at throughput at 0.5 nanograms per liter. We can't achieve that now with the new tubing, but the old one was 90 seconds. And again, you have to look up here, the change from less than 1 nanogram to less than 5 nanograms, so an increase of instrument detection limit is not that large of an increase. The slope changed slightly from 40 to 60 and 13,000 down from 17,000. This is the 4 products that I mentioned earlier. So we have the CVAA system, the Hydra 2, which is a modular design, AA. Here's the 7600. It's pictured here with the 2-rack auto sampler. The M8000, which is our cold vapor atomic system, 3 modes of operation, single gold, double gold, or just straight atomic fluorescence. And then here is our combustion system, our Hydra 2C, which is the CAA, combustion atomic absorption. Basically, any sample you want to put in a boat, liquid, solid, semi-solid, volatile, organic, you put that in the boat and it will give you the concentration of mercury in that sample without digestion. It is a really nice system. So with that, we're going to have you submit questions to my email address. It's jeff.forsberg@teledyne.com. And I'd also like to thank Mary Jo Wright. I want to give analytical acknowledgments to Mary Jo Wright. She is the application chemist that helped gather all the data on the SRMs and perform all of the testing for the smaller ID tubing. So again, I want to thank you for attending today's webinar. And if you have questions, please submit them to jeff.forsberg@teledyne.com. And thank you and have a great day.